Thanks everybody for being here. My name is Jared Griffith. I'm from Ruckus Networks. Been running with the pack for about 12 years now with them. And I'm excited to be here in Prague and talk to you guys about separating marketing's bark from reality's bite on 802.11be, or as we would all call it, Wi-Fi 7. So a quick recognition, does anyone know why I'm up here talking today? And I'll give you a couple of hints. It's not my dashing good looks or my witty personality, but about 15 years ago, I was a small business owner in Utah and had a lot of confidence, probably more confidence than skill set at the time. And I ran into a problem and I was about neck deep into alligators on a Wi-Fi project. And I was lucky enough to meet Keith Parsons, and if any of you guys have ever spent much time around Keith, you know that he has a favorite saying. And his favorite saying is, knowledge is like manure. If you spread it around, things tend to grow. But if you keep it all to yourself, it stinks. And so Keith, I'd like you to come up here. I've got a little gift for you. It's a programmable lightsaber, because I used to work in Keith's lab with him, and I was the Padawan and he was the Jedi Master. 15 years ago, Star Wars was a big thing, so. And thanks for putting on all these conferences, Keith. It's really been big to the Wi-Fi community. All right, so we'll jump into this now. Quick timeline. So 1997, 802.11 Classic, as a lot of people like to call it, hit the roadmap, ensuring us all a future career. In 2022, 2023, we now have the 7th generation of Wi-Fi, which is 802.11be, and the way things are moving, it is quite different than what the 802.11 Classic was. From my understanding, WFA will ratify this the end of 2023, and the IEEE will ratify in 2024. So, marketing stream of Wi-Fi features. So, new applications such as augmented and virtual reality, gaming, remote office, and cloud computing, along with a high number of users, has pushed along with new buzzwords like real-time applications, and you're going to see that a lot in Wi-Fi 7. Some of the new IEEE 802.11be standards are double the bandwidth, increased number of spatial streams, data rate of 40 gigabits plus, support of real-time applications, future support of massive MIMO, advanced PHY and MAC techniques, AP cooperation, but wait, that's not all. It slices, it dices, it mints, it'll turn the lights on and off for you, it cures coughs, colds, runny noses, and once you see all of the RU tables, and along with the MCS indexes, it'll have you buying David Coleman's next edition study guide faster than Wi-Fi 7 ever could be. So, I've always been a guy that has made my career where the whiteboard ends and the sidewalk begins. We're so far out in front of Wi-Fi 7 right now, this is literally the beginning of my sidewalk. I'm looking back at the marketing team. So let's talk about the PHY. And to set this up, I have a couple questions for you guys in the audience. Who in here has designed a Wi-Fi 7 WLAN to date? Anyone? Who's tested any Wi-Fi 7 clients to the APs? Coleman? Bueller? Anyone? Who's tested these features in the wild? Who's even seen a Wi-Fi 7 AP working? Well, don't worry, I brought a consultant to help us out. Ladies and gentlemen, I'd like to introduce you to Zoltar. He is definitely going to help us, and that's kind of where I want to do my safe harbor announcement. A lot of the things that we talk about today, they might change because full ratification has not happened yet. We're in a draft area right now. So just keep in mind that as we talk through some of this stuff, it does have the ability to change and push out to the 8th generation of Wi-Fi. So as we talk about extremely high throughput, we're scaling the PHY of the previous standards. Double the bandwidth, we now have 320 megahertz, double the number of spatial streams, 16 by 16. And we are introducing a higher rate MCS by adding 4K QAM, which will optionally be supported. Some of the revolutionary changes to the PHY is going to be generalization of the previous PHY headers, developing a forward compatible frame format, And when we look at the throughput effects, because we are doubling the channels, we're doubling the spatial streams, and we are increasing 20% by doing 10 to 12-bit assembling, and the QAM gives us a multiplier of 4.8. So with Wi-Fi 6, we had an available 9.6 gigs, which now theoretically puts us into the 46 gigabits capacity. Theoretically. Theoretically. So you ask, how fast will my Wi-Fi be? And I kind of love it that it's 802.11be because how fast will my Wi-Fi be? So I've given you guys an equation for a single spatial stream, 40 megahertz, or as they like to now call it, extremely high throughput, 484 tone resource unit with a single spatial stream. And some of the cool things about that is our available theoretical throughput is 344 megabits, MCS 13 on 4K QAM. When we look at Wi-Fi 6, the same configuration using 1024K QAM was 286.8, and Wi-Fi 5 came in kicking a cool 200 megabits at 256K QAM. So just looking at the way Wi-Fi is re-evolving itself right now with the tones and RUs and the MCS indexes, we as a professional community are going to have to start relearning these things. I feel another book coming on from Mr. Coleman, but we really are. The days of PHY, data, and MCS really is evolving quite a bit. So 4K QAM, when I heard about 4K QAM, this is one of the things that excited me the most. And so it's a dream come true, right? Or is it? So when we start looking at 4K QAM, the SNR at the receiver side to get 4K QAM needs to be about 40 dB, which really is not conducive in most Wi-Fi environments. But don't worry, it can be achievable through beamforming and beamflex. Shameless plug for Ruckus. So the other thing is AP with many antennas that serve only a single client station with few antennas. Multi-user transmissions will not be used. The number of client spatial streams will be low. 4K QAM will be optionally supported by extremely high throughput. Even though rarely achievable, probably less than 10%, it is exciting and a building block going forward. So some of the issues that we've had with wide spectrum legacy approaches in the past, all the transmissions at different subbands are fully synchronized. The channel access is mostly controlled by a primary 20 megahertz subchannel, which means the whole wide channel is blocked if the primary channel is busy and the rest of the subchannels are idle. So we have spectral waste. Operation in wide channel consumes more power that is crucial for mobile devices. And if a device only supports single channel operation, vendors like myself cannot mark and indicate on a box higher throughput than what the standard is. But don't worry, we have 320 megahertz channels. So we can double the maximal nominal throughput with respect to Wi-Fi 6 or 11AX. In 11AX, we had 20, 40, 80, 160, and 80 plus 80. With Wi-Fi 7, we will support all of that along with 160 plus 160 and non-adjacent 160 megahertz channels, similar to the 8080 of 11AX. So we could also maybe support 160 plus 80 as partial bandwidth mode of the 160-160. Non-contiguous bandwidth provides a high bandwidth if no non-contiguous spectrum is available. It's great for marketing, not for deploying in the enterprise or dense environments though, but it is achievable. So some of the open issues that we see today with extremely high throughput PHY is, will it be possible to use higher data rates when stations are located different distances from the AP and have different capabilities, mixed mode? Channel sounding will become more complicated, and with 16 spatial streams, that will never happen, and the wider spectrum, it is not clear if 320 megahertz channels will be advantageous in dense scenarios, but we in this room, we're professionals and we already know the answer to that. It will never fly. There will be more problems with frequency selective interference and fading. Achieving the gain of multiple antennas requires an advanced scheduler, algorithms that may cause increase in the cost of the Wi-Fi equipment. As a manufacturer, we're all right with you guys paying more for the APs, as long as we don't have to pay more for the parts. So the new PHY performance must be tested in real scenarios, different stations, locations, moving stations, and limited number of antennas on the station. Testing the whole non-whiteboard theoretical world that we're so used to in the marketing department. So another innovation is the EDCA with 802.1 time-sensitive networking features. With 802.1, that is an Ethernet format, and so we're now trying to bring that into the Wi-Fi world. So the reason why is we want to support real-time application. So we've got to figure out the best back-off procedures to assure timely access to the medium, additional access categories, admission control, and medium access control. So 802.1 TSN cannot directly apply to Wi-Fi networks. Anyone curious why? Because we use carrier sense, random access, exponential backoff, and we are prone to interference. And it's impossible to guarantee performance with regards to latency and reliability due to those things and the connection. So we have two types of scenarios that we usually deploy Wi-Fi into. We usually have a hotspot or a home type environment. And we also have an enterprise or a carpeted environment. So some of the problems that we have in the hotspot or home is there's a lot of interference and contention for the channel because we do not own any of the airspace and we are not on an ESS. It is just everyone with their own individual BSS. And performance is always going to be limited by interference. So when we look at using an ESS or an enterprise grade, some of that can help be controlled by TSN requirements. So low latency and high reliability might be achieved. So as we talk through, before we go any deeper into this, let's look how a packet is typically transmitted. As you can see in this graphic, there's typically 4 stages. One is the scheduler, where the packet is queued and then it starts contending for the medium. Once the AP is contended for the medium and got access to the channel, the transmission time comes into play, where the transmission of the first packet starts. In the case of interference, if there is a collision, it starts a retransmission, then the ACK is received and the final transmission packet is completed. And as we know, that is where we have lived the majority of our life trying to figure out why voice over Wi-Fi calls suck. So as you can see, the packet tends to take more time in some of the stages versus the others for different traffic conditions. For example, in EDCA versus OFDMA, there's more time spent in contention and retransmissions. The reason is because OFDMA assigns RUs for each station transmission. There is no question of contention or collision. For EDCA, it must get access to the medium, involves backoff, so there is more time spent here. So now we're looking for Wi-Fi7 EDCA improvements for real-time application also. Worst case latency must be reduced for RTAs. If an RTA packet is small and infrequent, the required worst case latency can be achieved without packet losses. An example would be gaming. The latency is worsened for gamers when a video stream is introduced. Part of that problem is the video is best effort access categories. Some of the solutions being studied today to help achieve this is update to EDCA to use alternative voice queues for real-time application trafficking. Introduce new access categories, persistent channel allocation, and predictive channel backoff count. Before the packet is even queued, it might be possible that the RTA traffic is small and periodic. As the packet can arrive, it could be predicted beforehand. So reserving the channel with a null packet by the station if the packet arrival is expected soon. We're going to have modifications to the transmission opportunity rules. Allow the use of TXOP of any AC to send RTA. Don't you love our acronyms? Say that 7 times fast. As soon as possible. The AP may recapture the transmission opportunity to deliver real-time application traffic. So this is a hypothetical proposal for a new access category sitting above the voice queue. for the real-time applications. Along with that, they would have to enhance or develop a better time-aware shaper to be able to handle real-time application. So now they're also talking about enhanced OFDMA. So 802.11ax, or Wi-Fi 6, had some drawbacks. One, it wasn't all that flexible. It allowed the AP to allocate only one resource unit of a predetermined size to a client station. It did not support direct link transmissions. It reduced spectrum efficiency due to fixed RU sizes and unused allocations. It degraded in dense environment for performance, and it increased latency prior to the transmissions. Wi-Fi 7 is looking to address some of these challenges by preamble or channel puncturing. And I know the first time I ever heard that, I got pretty excited about it too. So multi-RU scheduling to one station, OFDMA with direct link, and OFDMA for real-time applications. So as we get into preamble puncturing, it allows transmissions on higher order channels, even though the 20 megahertz subchannel is busy, non-primary. So only in 20, 40, or 80 megahertz chunks. And what we have here is a graphic. So this is 160 megahertz of spectrum. And it's built up of two 80 megahertz channels. So we have a primary channel of the primary 40 that is the anchor for the entire transmission. The secondary channel in this situation is busy. So in 802.11ac, in this environment, we would have 60 megahertz of channel waste, or spectral waste. So what happens with channel puncturing is, in the event that this would happen, that the secondary 20 of the primary 40, I love where this is going, is busy, we could still use the secondary 40 of the primary 80 to be able to puncture. And that sounds really good. But is it? So some busy 20 megahertz subchannels can be used and punctured. The frame preamble is not transmitted and RUs are not allocated in these subchannels. In dense employment, this will allow the channel resources to be more flexible and efficient, but there are restrictions. And some of those restrictions are 80 megahertz channel, only 120 megahertz can be punctured, and it cannot be the non-primary. Preamble puncturing resolution is 20 megahertz in the extremely high throughput PPDU. Puncturing a subchannel smaller than 242 tone RU is not allowed. 160 megahertz or 80 by 80, the same can be done for the primary plus the whole secondary 40 megahertz channels. None of these parts of the secondary 80 megahertz subchannels can be punctured. So we're stuck at 80. It extends the operation for 320 megahertz channels and improves it, enabling puncturing for the single user frames. Utilizing OFDMA, enhanced features to ensure low latency and jitter for delay-sensitive traffic. These are some of the real-time applications that we would use this for. The current APs can centrally manage the upload and download transmissions. However, additional enhancements are needed for low latency traffic. Went too far, sorry. Interference mitigation for the download and upload. Traffic vulnerable to interference is that it causes collision, defers channels access. Some of the ways that we are going to try to mitigate this is the allocation of dedicated resource unit to a station when the data becomes urgent. Understanding traffic parameters, including remaining lifetime for optimal scheduling of channel resources, and only stations having upload traffic will transmit in the dedicated RUs. It will speed up collision resolution process and increase the RTA of the stations in a network by up to 50%, or according to any of the marketing geniuses behind the white papers. Some of the open issues that we might have is flexible channel puncturing may lead to spectrum fragmentation. Efficient usage of OFDM requires a redesign of the scheduling policies, and it's not as straightforward as LTE since RUs form a complex structure. Due to the flexible RU allocation in Wi-Fi 7, scheduling is more challenging already. This will not be defined as part of the standard. Resource allocation now needs to depend on the types of traffic to be delivered. QoS parameters need to be considered into the scheduling. Delay tolerant flows need to be delivered in the RUs with the highest spectrum efficiency. And RTA packets need bounded delays to ensure the lowest latency. Which moves us on to the MLO, or the multi-link operation. Grab some water. Who's asleep? I am. So, Wi-Fi7 or 802.11be relies on the defined .11 AD and AY multiband operations to achieve better performance, allow sending packets concurrently on multiple channels. And we get all excited about this because we think 2023 Wi-Fi7 is going to deliver this. Back in 2016, both Qualcomm and Broadcom were already doing this. They were doing it to solve the same problem that it's doing today, and that is for real-time applications of gaming. And there was a company called RealTime who was building cards to be able to do this, and it was working with both the manufacturers. Intel found out about this. They didn't want anyone else to have the technology, so they bought RealTime, killed it, and the idea of MLO at that point stopped moving forward. So it's not as exciting as we think. It's already like 6-7 years old. But what it will do is aggregate various numbers of links on differing channel widths, separating control and data planes into different bands, and a low band and a high band. One for management, one for data. Can anyone already see the problem with using multi-link operations and the fact that we always have problems with client driver subsets? I can. So an MLD, or a multi-link device, consists of several affiliated Wi-Fi devices. Each has its own PHY interface to the wireless media, but with a single interface to the LLC layer. The upper layer protocols consider the MLD as a single device. Despite having multiple physical radio interfaces, the MLD will have a single MAC address. So the frame formatting will change somewhat, but not a bunch. Two possible modes of the multi-link operation. We will have a restricted link switch and a dynamic link switch. And all of that is just in theory as of this day. So some of the type of the MLOs are multi-link single radio and enhanced multi-link single radio, or EMLSR, as we didn't need another acronym to add to our repertoire of words. So non-simultaneous transmissions and receives on the ML radio, or non-STR, MLMR, can be simultaneously received and transmit over 2 or more radios, but only under certain constraints, separate frequencies, and they can be received. So this is an idea of what it might look like, and we have a couple different modes here. We have a duplicate mode, and then we have a joint mode. In the duplicate mode, everything is sent across 2 streams, whether it be 2.4.5.8 or 5.8.6, or 2.4 and 6. It depends on the chip manufacturer and how they're going to develop their low-level chip code. In the duplicate mode, everything that's sent on one will be sent on the other, and anything that is not needed and hasn't been received will be discarded. So there you have your spectral waste on the duplicate mode, when you could be splitting up the data and sending it over 2 streams instead of 1. On the joint mode, the lower latency transmitter distributes the frames over all available links, and while the management will be sent on another. There is some proposals at the WFA and the IEEE called the conditional packet duplication mode, where the MLD initially tries to deliver a frame only via 1 link. If successful, after some time, it replicates the packet and tries to deliver over the other links. Sounds like EDCA. So anyway, that is probably the one that'll win because it'll have the most lobbyists and it'll be tied to some money from someone somewhere. So some of the open issues that we have on the MLO: coordination between links, optimization to reduce worst case latency and enhance reliability for RTA, synchronization of the channels, mathematical models for synchronous and asynchronous channel access modes, minimizing channel wasting and head-of-line blocking delays, restricted time TWTs feature provides insufficient guarantees for practical use. For APs, it is optional to offer restricted TWTs and for stations to join with them. Client drivers green diamond matrix. So when we look at all of that and everything that the ML is going to bring us, this is what we get. So as we talk about Wi-Fi 7, and I thank everyone here today, I know that we didn't go down to the molecular level like many people in this room want. It's because I don't think that level quite exists yet. That's still in development. People are working on it. And we're talking all about theoreticals today. But I would like to thank everyone who came to Prague, who came into my presentation, and thank Keith for the opportunity.